the first unit, good design versus bad design. So let's solve a problem in two different ways. Then we compare. Okay? So which one is better? So we did this kind of thing several times. The problem is a simple one, Fibonacci numbers, very famous numbers, given recursion formula. So this is the recursion formula for the Fibonacci numbers. The first two, the base cases, given, then we have that simple recursion. Okay, Fibonacci numbers. All right, now we need to calculate. So given any n number, we need to find f sub n, Fibonacci number. Okay? So the sequence, so the first few numbers sequence like that. So here you can see it's not very easy to find some nice rule we can use. Okay? So it looks like it's not easy to find some pattern here. Right? Yeah. To find this number, so let's consider, what we can do. Okay, yeah. Basically, two different ways. The first one, we can find an algorithm, or just from the formula, we can write a program to solve it. Yeah, write a program, simple program, we can solve it. But second way, solve it mathematically. Is it possible we find a math formula, okay, for Fn? Yeah, so if we have a formula, now we just plug in, given n, we plug it into that formula, we can find that number. Yeah, so these two different ways. Usually, for many problems, the second way may not work. Yeah, because many times it's very hard to find a math formula for it. Yeah. Actually, I can write a recursion formula easily, and then nobody can find a math formula for it. Okay? For example, I put a square here. Right? Put a cube here. So who can solve it? Yeah. So it's very easy. Someone can write a recursion formula that nobody can solve. Okay? So that's why the second way, only for a very special cases, we can solve. Yeah. In general, we cannot solve. Yeah. But we can always solve writing a program. Yeah. All right. So let's do the first one, the easier one. Yeah. Straightforward implementation. Yeah. So this is our Fibonacci function. See? Yeah. Recursion, two base cases. Other than that, recursive function call. It's so easy, right? Yeah. But the question is this a good one or bad one? Yeah. So after we learn this algorithm class, we need to know if this algorithm is a good one or bad one. Yeah. If it's a bad one, we should not use it. We should find a better one. Yeah. So here, it may be hard for you to see that, right? Yeah. How can you see it is a good one or bad one? So we need to do some analysis. Yeah. Yeah. So no problem. We can find a correct solution, but we are not satisfied with the correct answer. We want efficiency. Efficiency, yeah, for this class. The most important thing we need to study, efficiency. Okay, all right. first we need to know if it's good or not. If it's not good, why it is not good. We need to know the reason why it is not good. Okay, all right. Answer, it's horrible. Yeah, really bad. Yeah. Okay, really, really bad. Okay, yeah. So how bad? Yeah. So we will see it. Yeah, how bad it is. Okay. Yeah. Here, I give you your first programming project. My plan for your first programming project. This problem. Okay? We compare good one and a bad one. Yeah. Compare efficiency for two different algorithms calculating Fibonacci numbers. Okay? One is this one. Yeah. Yeah. Simple, but very bad. Yeah. Another, our second one, we improve it. Okay. So we make it efficient. Yeah. So you write these two programs. So in your project, you need to do experiments. So you find, so given n, right? So given some n number. The n number should be large. Yeah. If it is small, it's hard to compare. Right? If it is small, it's remember, when we compare efficiencies, we want to compare when n is relatively large. When it is small, because overhead may take more time. So we don't want to look at the overhead part. Yeah. So when the n number is relatively large, you need to run two different programs. But in your program, because we do experiments, so I want you to calculate, to clock the execution time, the running time for each function. Yeah. Because you use the same machine running two different functions. So you can compare the execution time. Right? Yeah. Yeah. I will give you more detail about this project idea. Okay? All right. How bad is the algorithm? Let's draw a recursion tree to find the reason why it is very bad. Okay. All right. So let's start with this recursive formula. We only need to calculate Fibonacci number of 6. It's good enough to see the problem. Right? In order to calculate Fibo of 6, you need to calculate 5 and 4. Yeah. This number for 5 and 4. Okay? So let's draw a tree. In order to calculate Fibo of 5, we need to calculate 4 and 3. Right? Similarly, so we have a tree. Okay? So we have a tree like this. Remember, the recursion inside your program, you need to use the stack. You push, all these functions into the stack. Okay? So then you calculate. So you have a very deep stack. See? Very deep stack. Okay? All right. Now, can you tell me the problem from this tree? Any problem we can find? Right. So obviously, some numbers repeated many, many times. Okay? Look at the Fibo of 2. How many times it is repeated? Okay? How many times Fibo of 2 repeated? Okay? If you draw a big tree, let's say 100, you can see many numbers repeated too many times. That's not efficient. Okay? Because we don't need to repeat. If you calculate Fibo of 2, the next time when you need, you just use it. Why you need to recalculate it? Right? So the good one, we should make sure each number we only calculate once. So this one, you calculate in a large number. So if we do some analysis, you will see the number of basic operations is an exponential function. Exponential function. That's big. Exponential function. Okay? Higher than any polynomial. Yeah. So we did in the last lecture. Exponential function dominates any polynomial function. Okay? Yeah. So that's why this algorithm extremely slow. Yeah.
Can you say that again?
Exponential function dominates polynomial function. Okay? Dominates any polynomial function. Exponential function. Yeah. So that's our conclusion. Before. Okay? All right. Solution. You can see remove the redundancy, right? Remove the redundancy. The question is, how do you remove the redundancy? How do you remove the redundancy? Yeah, save, right? So save the values, that means you use more space, right? You use more space, because when you save, you need to use storage space. We pay, yeah, we need to pay. We pay on the storage space, and our gain computation time. We reduce the computation time. So this actually is a good strategy. So this strategy we will use to solve many problems. Yeah. So in this example, we will see this strategy the first time. So we pay a little more in space, and we get big gain in running time. All right. Method 1. All right. So, yeah, actually the method, yeah, we should say method 2, right? I mean the previous one, method 1. Yeah. This one we can treat as method 2. Yeah. All right. Iterative algorithm. Iterative. All right. So we use the array to store this number. So we calculate that array. Okay? Yeah. We use array to store all the intermediate values we will store in this array. Okay? For example, when n equals 100, we need to calculate from 0, 1, 2, 3, all the way up to 100. All the intermediate values. Yeah. So that's the meaning of that iterative algorithm. Okay? All right. So the code like this. Right? Your initial, so initial values like that. Then when you do this, when you calculate fiber of higher number, you always use the fiber of lower numbers. They're already known, right? Because you calculate all the way up. Okay? You know the Fibonacci number of the lower, relatively smaller size. Yeah, let's say we can use the size here. Okay? And find one of the current size. Yeah. So this is iterative. It's not a recursion, right? You can see we do not do recursion. We do not do recursion. So we do not use deep stack. There is no deep stack. And another thing, there is no repeated calculation. Each number we only calculate once. Okay? Yeah. So it's a good solution. It's a good solution. Yeah, definitely it's a good solution. Okay. Can you tell me, if we use big theta, what big theta we can use to describe this algorithm? Big theta of what function we can use for this algorithm? Big theta of what function? N. Yeah. Yeah, linear. N. We go through, we along, because one for loop, right? Not too nested. One. You go through from beginning to end. So each number you do one operation. Yeah? Linear. So obviously it's a linear. Now you compare. the previous one exponential function. Yeah. I haven't done the calculation. Yeah. So if you're interested, so at some time I will show you why the previous one we get an exponential growth function. The growth function exponential. Okay? Yeah. So later at some time I will show you that. How can you compare an exponential function with this linear function? Huge difference, right? So that's why I said the previous one is a horrible one. Exponential. Okay? All right. Method 2. This one is already very good, linear. Why we need a method 2? Yeah. Actually, the method 2, it's a similar algorithm with similar property, but the thinking is different. The idea, the thinking is valuable. So the method 2, performance-wise, the first one, the second one, very close. The first one, second one, very close. But this method 2, or our method 3, yeah, so probably should use, 2, 3, that exponential one is 1. Okay? Yeah. Anyway, yeah. So because I want to use this chance, talk about method 2, because there is a big idea behind it. Big idea. Very valuable, big idea. So I want to introduce in this example. Right. What's that? We do recursive algorithm. Yeah. Yeah, because here we don't want to drop recursive algorithm. We know recursive algorithm is powerful, right? Yeah. Because if you try to avoid recursive algorithm, sometimes some harder problem you cannot solve, because the only way you can solve recursive algorithm. So we don't want to drop the recursive algorithm. We still want to use recursive algorithm, but we just remove the redundancy part. How about that? Without redundant calculation. If we can do that, then in the future, even when we using the recursive algorithms, we can improve its performance. So that's the value for this new method. Okay? So how can we do that? All right. Use an array. Yeah, similar to this one, we still use array to store calculated values. So for the intermediate values, after we calculate them, we do not throw away. Okay? So let's keep them. Yeah. So next time, we just retrieve from the array elements. Yeah. Trim from there, then we avoid redundant calculation. Okay? So the idea is very simple. Okay? Make sure no value is calculated more than once. Yeah. So that's easy. Yeah. We know after we store, we can see it easily. Okay. All right. Now the implementation. This is the code. Okay. So we write new way to write function. So you can see we modify the previous recursive algorithm, but here we use a special array. So here I call non-F array. Okay? Non-F array. All right. So at the beginning, when you start the non-F array, all initialized to be 0. But initial. So initial value for this non-array, initial 0, all 0. Okay? All right. So then you can do recursion. Yeah. All right. If it is 0, this value is, because if it's 0, you need to go down. If the value is greater than 0, it's known. That means you already get it. Just return the value, right? You don't need to do any calculation. It is already known. Greater than 0 means it is known. Okay? Equals 0, unknown. Equals 0, that's our initial value, unknown. Okay? The Fibonacci number for that size unknown. Okay? Yeah. So use this to tell you if it's known or unknown. All right. If it is unknown, other than 2 base cases, you can call recursive function. It's no problem. You can call it S equals that. Okay? Function recursion. But you can see in this way when you write, each Fibonacci number only calculate once. Why? Because after you calculate, you get S, you assign S to that known array, right? Known element. Known F is assigned to that number. So you only calculate each Fibonacci number, you only calculate once. After you calculate once, you assign to this element, it is known. Next time, you do not need to calculate, you just return its value, right? So this way, so try to look at the idea. This idea has a lot of significance in algorithm design. Okay? Yeah. Very important. Yeah, try to see it. Yeah. Try to see it. Yeah. Now compare. Okay? Can you compare these two? Yes. This also big theta of n. Also linear. Because look at the array element. Each array element you only calculate once. So definitely although it's a recursion, but eventually you also get a linear algorithm. But can you tell me if we really, although both linear, can you tell me which one is slightly better or which one slightly faster, slightly better? Can you tell me that? Storage, yeah. So storage, yeah. But compare the overhead. Which one uses a little more overhead? The second one uses more overhead because stack. Okay, recursion you need to use a lot of deep stack, right? You have to use the stack, right? And this one, no stack, no deep stack. Okay? So performance-wise, this one slightly better. Yeah. Actually, we can, because the stack, from the stack point of view, significantly better, we can say, right? Storage usage, significantly better. Okay? Yeah? Yeah. All right. Yeah. Let me also put these two methods in our project 1. Yeah. That exponential one, we need to compare. Yeah, both beat, significantly. But if you look at execution time, I believe this one will a little faster than that one. Right? A little faster. Okay? Yeah. So we want to see it. Yeah. Stack. So you can see the cost we pay, recursion, that stack. But the reason we don't want to throw away this one, because sometimes it's hard to find that solution. Okay? Think about, for the Tower of Hanoi, can you use this iterative method? Nobody can use that, right? How can you find the iterative method to solve that Tower of Hanoi? You cannot. Yeah, nobody can do it. Yeah. Sometimes we have to use this method. Okay? Yeah. So we cannot avoid that stack. Yeah. All right. This idea is a big idea we used here. All right. So we call it dynamic programming idea. Dynamic programming idea. So this is a big topic, chapter 8. Yeah. So we will have a chance to study, but at very late, probably the last lecture, if we have chance, we will learn that. Yeah. But this is the first time we see this idea, dynamic programming. Yeah. It's a big, important topic. Yeah. Yeah. We can also call dictionary method. So why you call dictionary method? We use a dictionary. So here, this array, we use it as a dictionary. After you calculate its value, next time we look up in the dictionary. That's the way we use dictionary. So we do not recalculate it. We just look up in our dictionary and find the answer. Yeah. So also that. Yeah. All right. Yeah. So